Hello, everybody, and welcome back to Dr. Bob's Operation Get Good Briefing Week 2 edition. Sorry this is a little bit late. Had to get all the kinks worked out. But here we are once again, and we're just going to dive right into our first problem. This is ACM contest scoring. This is, the reason I chose this is, one, it's a fairly easy problem, and two, it is also going to be able to show you how the scoring works at the contest. So the idea is every problem comes in, you either get it right or wrong, and then if you get it right, you get credit for the problem, and then the time it took you to solve that problem is counted in minutes, and it's however long from the beginning of the contest that it counts. Then if you get it wrong, you get 20 minutes added to your score, but only if you have eventually solved that problem. So the scoring criteria are which problem, how many problems did you solve first, and then if there's a tie for that, how many minutes did it take? So here's an example of potential solutions. With this one, they got problem E right in 3 minutes. Then they got 3 submissions that were wrong on A, C, and B. Then they got A wrong, then they got A right at time 200. So that was 2 wrong submissions plus 200 for a total of 240. 250 is another wrong solution, and 300 got problem D, which was right. Now D had no previous wrong solutions, so you're just going to get the 300 points. So the total for that would be 300 plus 240 plus 3, or 543. As you can see in the example output, that's the way it goes. So the way this problem is formatted, you've got a number, which is the minutes, the problem, and whether they got it right or wrong. So essentially what you need to do is store how many wrong attempts there were for each problem, and the time at which they got it right. And the problem itself says that there will not be any wrong submissions of problems after a right submission, which is good, although my solution accounted for that. So let's take a look at my solution real quick. This is a Python solution. I decided I would use a dictionary. So this is a dictionary object. And the reason I did that is so that I could just associate each tally of attempts and minutes and things with the problem letter. So I could use the letter as the index into the array. So I get the first input, and then I check to see if it's the -1 at the end, and if it's not, we split the line, and then we split it into 3 pieces. The first data 0 in this case would be the number of minutes, and so when I do data 0, I get int data 0 right here. You can see that happens. Data 1 is the letter associated with the problem, and data 2 is wrong or right. So I say if it's right, if it's not already in the problems, what I do is I'm storing a tuple, which the first value of which is a Boolean telling me whether or not they got it right, and the last part is how many minutes. And if it's already in there, I just tell it to add the minutes from before, because if it's not right, then I check to see, if it's not in there, I add it in with a false and a 20-minute penalty. Otherwise, I go false and an additional 20 minutes on top of what's there. Then finally, after putting together all those problems listings, I get together a count of problems correct and a total number of minutes. Just go through for all of the problems. I check to see if they got it right. I add 1 to the count and add to the minutes. So 0 would be the first element of this tuple, and 1 would be the second, which is the total minutes. And then for the end, I just tell it to output the count and the minutes separated by a space. It's a very straightforward problem. Alright, so let's move on to the next one. We've got Holy N Queen's Batman. So this is a variation on what's called the N Queens problem. The idea is counting the number of ways that you can place N queens on an N by N board such that none of them attack each other. That's that's the classical problem. Now with this one, there are some holes in the board. And now if you read the problem, it says that queens can still attack each other across holes, but they just can't be placed on a hole. So the difference between these is you just can't place a queen on a particular hole. I think the problem would be significantly more difficult if queens couldn't attack through holes. That would be significantly more difficult. So the idea is, so one thing is, since you're only ever going to have one queen in every column, you can store a solution to this as which row you put each queen in every column. You can do that. So there's like a bunch of numbers. Now, as you place a queen in a spot in a given column, well, the column is already ruled out, but that's just ruled out by the data structure. The row is already ruled out, or the row gets ruled out going horizontally from that point on, and then the two diagonals going up and down from that queen get ruled out. Now, one thing you'll notice about this is that we can have up to 1,000 board descriptions, but each description starts with a line containing a pair of integers 3 less than n less than 12, and m less than n squared, indicating the size of the board and how many holes. And then each hole is unique in the board. Now, one thing I note is that since it's only got up to 12 values, or 12 board values, it's reasonable to actually go ahead and generate all the solutions for 1 to 12, and then count the ones that don't contain values at those spots. You can do this fairly easily in Java or C++ pretty quickly, and depending on your timing, you can do it one way or the other. But when I did this with Python, I ran into some time issues again, but I was able to get my efficiency down, and I want to talk about that efficiency. Okay, so one potential way of doing this is to literally just write a program that gets all the solutions from 1 to 12 slowly, and then copy the results into your code. That was the first approach I tried, actually. I just wanted to hard code the table. The problem with that is that there was a maximum size on the file you can submit, and that's 128 kilobytes. So I then tried compressing it down using various techniques. I could have actually gotten it under the proper limit, but I decided I would try to make it a little more efficient. So here is the solution, and some of this is going to look a little foreign. So here's my nQueens function. It just calls a helper function that gives me n, and then 0, and then an array of nothing but -1, and then an array of nothing but zeros, all of length n. That's one of the little shortcuts you can use in Python. So these variables here, they are called NIS and A. I have names for them in my head. N is just the n from nQueens. I is the iterator through the columns. S is the current solution, and A is the attacked squares in the remaining side of the board. Okay? Now I say if I equals n, that means we've iterated through the entire list and we have a solution. What I do is I return this. Now what this is an array containing the contents of S, but I do x for x in S, and the reason for that is because it will copy the array if you do that. If you don't do it, it will just do an array containing the array S. And when you make any changes to S, it will mess it up again. I don't know why I have minus J here. I meant this to be -1, but it still works. So then I say, okay, here's my return value, which is an array. And then I go through for 0 to n, and I check to see if the next column, or if the column I'm in, has a free spot or a non-attacked spot at position J. Now the way I do that is using this. This is going to seem a little weird, because this array right here consists of a bunch of numbers, but those numbers are going to be used to list whether or not an entire column or the squares of an entire column are being attacked. And I do this using what's called binary booleans, or at least that's what I call it. So, for example, let's say that I had a row where the first item and the 5th item and the 7th item were being attacked out of 8. So one thing I could do is I could just have true, I could have an array of booleans that's true, false, 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 true, false, true, false. I could do that. Now the reason I don't use an array here is for the same reason I create that copy later on, so I don't have to sit there and copy everything over, because when you return array because when I go to the lower levels, or the later when I go to the later portions of the board, I cut off the portions of the board that we've already used. So the array actually gets smaller as we go down the board. So what I did is, since it would copy numbers, I just used a number. So one thing you might do is use a binary number like that, and that's pretty cool. Now, the way you would extract values is using a bitwise operator. So what you could do is, to get the value in this position, you could take a value that only has a 1 in that position, and then AND it together using a bitwise AND. So it's going to take each pair of corresponding values and create the result of using the AND operation. So if they're both 1s, you'll get a 1. Otherwise, you'll get a 0. And then all you have to do is make sure that this value is not 0. And if that value is not 0, then the Boolean you're selecting is true. If it is 0, you get false. And so like if I were selecting that value, I would get 0s across the board because there's no matching 1s. And so that would be a false. Now, the only difference is, I said the 1st, 5th, and 7th positions were on. In my representation, I actually have it backwards. It goes like this. And the reason for that is because when I come in here, get my code up again. When I come in here, what this is 1 bit shifted j times. Well, if j is 0 for the 0th section, then this will not shift the 1 at all, and it'll leave it in the last position. And the same thing for 1, 2, 3, and so on. Now A0 here, this means the first element of our attacking row, which means the next column that we're on. And in the next version, I'm going to eliminate that column. So then, if we have a blank spot here, or a spot that a queen can be placed, we place the queen there in our solution. Then we create an array B, which is all of the array A, the attacking array, except for the one we just put the column in. Okay. Then I create a row that says to continue. Now this cont equals true is one of my little tricks here. The idea being, I'm going to fill out the rest of the attacking grid from placing this queen, and then if we notice in advance that one of our columns is going to be completely full up, we're not going to continue from here. We're just going to back right up. Okay? So we go through and we go for every value in the columns. We check to make sure that so if there's something to be placed on the upper diagonal, we go ahead and place one there. And the way we do that is with the OR function. So just like before, if you have a set of variables like this, 0, 1, 0, 1, and we want to say we want to say that our spot at position 3 here is now being attacked. Well, we will take our 1, shift it 3 bits to the left, which results in that, and then we do an OR, which means everywhere that we have either a 0 or a 1, we get the remaining values. So we do it like that. And so that just sets a Boolean to 1. Alright? To set a Boolean to 0 is a little more complicated. What you usually want to do, if you want to set one to 0, is you take this value and then you take the bitwise not with the tilde, and what that's going to do is flip all the bits, right? And then you do an AND. So let's say we wanted to remove this bit instead. So we do that, and we do an AND, so we get ones, we get a 0 here, a 1 here, 0, 0, 0, 0, 0, 1. So that removes it. Alright, back to the code. Did I say I think? Okay, there we go. Similarly here we say in this particular column or in this particular row we're going to stay on the course. So here we're going up in the column by k minus 1, where k is the number of times we've moved to the right. So the idea is we start here at k equals 0, or we're moved up by 1, or by k plus 1, I guess. And then where k equals 1, we move up further and also move up to a higher row. So that's what we're doing here. Here we're just staying straight along the side, and here we are moving down and to the right. Finally, this is where we cut it off. I say if b sub k, the one we just finished messing with, is equal to 1 shifted to the left n times minus 1. So what that's going to do is that's going to be 1 followed by a bunch of zeros. You subtract 1 for that, you're going to get a 0 followed by a bunch of 1s. And that list of 1s is all 1s for that column. So that tells you that the entire column is under attack and there's no place to place the next or any sort of queen there. So we can cut that off in advance. Then, if we're supposed to continue, I go ahead and get the end queens from the rest of it. And this is the RET, which is our return array. So what we're doing is we are adding the array we get here to this array. So this is an array of arrays, and so we're going to have an array of arrays out of this. Each individual array represents a solution to n queens for that n. Then what I do, because there's a reasonable number of solutions. The number for 12 is just like 12,000 or so. So what I do is I have this dictionary again, and then I say, I guess it didn't need to be a dictionary. And I say, for I in range 1 to 13, which gives me 1 to 12, I have the solutions equal n queens I, so it just loads the solutions. And then I go through, I grab n and m. N is the number of queens, or is the size of the board, and m is the number of holes. And I covered the case n equals 1, even though, again, I didn't need to. And then I said, I'm going to read in all the holes. So that is, for m lines, read in the line, split it, put the integer value of the first one in the first one, and the integer value of the second one in the second one. So that's our holes. And then I put the count at 0, and I say for x, and then I go for all of the things, all the solutions of length n. I decide whether I need to count it. I start out as true, and then I go through for all the holes, check to see if the value in the column it specifies is the same as the row it specifies. And if so, we don't count it because it's in a hole. So we're not going to count that solution. And it breaks out. And then if we're not supposed to count it, or if we're supposed to count it, we add 1. Then we just print the count and read the next line. Read the next thing. Alright, moving on to the last one. Make this quick. Fire. So you got a bunch of... you've got a maze here where you are an @ symbol, and there's a star representing fire, and walls representing... these representing walls, and you've got the floor. So, and the idea is to determine, can you get out, and if so, how fast? Out would be anywhere on the edge. So, one key insight I made is that in order to escape, there's no reason for our player to ever backtrack. Not ever. So what you can do is you can treat the squares in which your player has already been as if they are fire. Okay? So what we want to do is we want to keep track of what steps we can, or like where our player could possibly be after n steps, and there's no reason to backtrack. And we also need to know where the active fire is going to be. So we want to look at the fire, and as it's growing outward, we continue to add more and more spaces where the fire can be. So once again, I have another solution. I wrote one in Python, I wrote one in Java. I could just do the Java one. But basically I said, I had a couple of utility functions, and then this I used to convert the array into an array of integers rather than strings and characters, because strings carry a little overhead, and I wanted to make sure that my program solved it in time. I first grab the number of runs from the input, and then I say, okay, for each run, what I'm going to do is I'm going to create a set. And I do the same thing in my Java solution. I create a hash set containing integers. Well, in this case, I create a set for tuples. So I have lit, this is my set of lit spots, and I have my loc, which is my set of locations where the player can be. And then I say, read in the next line. It'll tell me how many columns and rows, because of course they did columns and rows. Anyway, and then this is my inputting the the maze. I say for dx, so dx is the value from this array up here for x in input from 0 to column. So it made sure I got just the first columns characters of the line, because sometimes you have input that has carriage return line feeds or just line feeds or whatnot. You can have white space issues in your inputs. Remember this. And then so for each character I make an array containing the numbers corresponding to them, and then I do this for the number of rows. So it inputs, each time it inputs a new row. Then I go through for every row and column. I check to see if we are at, if the value is 2. If it's 2, then I have a fire and it's lit. If it's 3, I have a starting location, which is I and J, and then I add that location to the locations, and then I set it to 2, because I'm going to treat the places I have been as if they were fire, because there's no reason to backtrack. So then I say time step equals 1, and then I have the exit function, or the on edge function. So the inbounds function makes sure that we are inbounds for the map that we're using. The on edge function tells us whether we are at the top, bottom, left, or right. And if we are at the top, bottom, left, or right, like at the beginning, then we can leave. We can just exit. And that takes us one time step because we have to walk off the board. So I check to see if we're on the edge. Then, while we still have locations we can be and be alive, I create a new set of lit and locations. I go through for each lit location, and this is my little trick from last time where I iterate through a list of tuples to get the above, down, left, and right situation. I just did ni and nj for new I and new j with this right here, so I didn't have to use it, copy this in multiple times. And I go, if we are inbound, if the new I and new j are inbounds, and we have a 0 or a 3 at that location, there will not be a 3 because I replaced it, but yeah. If we have a 0, then we can spread the fire. So we're going to add the new location to the fire and set its value to 2. Then for the locations, we're going to go through the same thing. We're going to say if not exit and inbounds. If we're inbounds and our map, if we have a floor there, then we can move there. Oh, and I set it to 3. Okay, so yeah, I guess we are going to have a 3 there, so we're going to allow the fire to spread into the 3s. You could have made this a 2 and it would have still worked. And then I set exit equal to on edge map and ij. So I say if we're on the edge, so if any of our possible locations are on the edge, we're good, we can leave. So one of the mistakes I made is not having checks to see if we had found an exit, because this would run no matter where we were. So if I ended up on the edge at one point, it might not actually come back because it would get set to false later. So I put in this check and I made sure if we're exiting, break, if we're exiting, break, and so on. Then we add one to the time step and set the lit and locations equal to the new lit and locations, so that we're only ever dealing with the neighbors of the most recently visited or lit spaces. Then, if we have exited, I print the time step we exited, otherwise I print impossible. And it works. Alright. So I hope this helps you out a little bit. I will see you all later. Problems will be forthcoming. And good luck.